Switching power supplies are electrically noisy. It's just a fact of life. But some converters are more noisy than others. Hello, and welcome back. Today, I want to continue talking about switch mode power supply noise by looking at how the exact choice of components can impact the final performance of the device. Figuring out the component values is one thing, but translating that into an actual physical component is another. Today, I will be looking at the two main reactive elements. So let's start simple. The inductor. Now, most switching converters, at least the ones that do not use capacitors to switch voltages, will rely on an inductor to be charged and discharged with a magnetic field. We know from our previous analysis that the inductor is usually passed by a triangular current, which does help quite a bit. However, on one of its terminals, you will usually find the switching node, which can be a bit bothersome. So there are a few very important considerations when selecting one inductor over another. So to get the supply to work in the first place, you need to select the appropriate inductance value, the right current rating, and keeping the ESR low will help to reduce losses of the converter. But what else should you be looking out for? The first fundamental property of an inductor is to hold a magnetic field. But the exact way in which it is built will have a critical impact on where exactly the magnetic field actually lies. From this point of view, inductors are classified as unshielded. The magnetic core is widely open, the magnetic field closes all around the inductor, but it's cheap. Then you have semi-shielded inductors, where some measure is used to at least partially keep the magnetic field inside of the inductor component, usually using some sort of magnetically conductive coating. This is more expensive, but better. And finally, you have the fully shielded inductor, a component that has a complete core, either made of two pieces of ferrite, with or without some extra magnetic paste, or you can have a single mass of powder. So based on how noise sensitive your design is, usually there are quite a lot of constructive alternatives to choose from. Now, other than these examples, there are a couple more to highlight. You can have a toroid core, not very common anymore since it's quite expensive, and you can get similar benefits using one of the other constructions previously shown. And another interesting implementation is the electrically shielded inductor. So at the time of writing, I only know of one manufacturer that does this, Vishai. Maybe there are others, but anyway, this constructive technique will better shield the environment from the inductor's noise. But obviously, this will also make it more expensive than the alternatives. Now, I have an older video in which I go into a bit more detail on this topic, both the constructive aspects as well as measuring some inductors, so if you're curious, be sure to check that out. But just to reiterate, I tried measuring the magnetic fields on two different shielded inductors. So for this, I used an old buck converter I had lying around and placed it into a small frame that keeps the near field probe at a fixed distance. And the first inductor to test is a fully shielded ferrite inductor. Now, any good measurement starts with a noise floor, just to clarify what is and isn't part of your actual noise. And well, once we have that, we can turn on the circuit and remeasure. Now, this measurement by itself is not very useful, so next I proceeded to change the inductor, swapping it out for a powdered core component of the same inductance value. And then I recreated the setup and remeasured. So now we have three measurements on hand: the noise floor in cyan, the ferrite core in pink, and the powder core in yellow. So while the low frequency behavior is more or less the same, small differences do appear. There is a substantial difference above 100 MHz. The ferrite core produces a large peak, while the powder core doesn't. Now, this is not a generally valid behavior, but rather it's important to observe that each specific inductor will have a more or less significant difference in its behavior. When changing order codes, the exact behavior might be different. Next important topic to consider is the inductor's equivalent model. So, as previously mentioned, other than the inductance, the inductor has an ESR, which is comprised of its DC resistance and the AC dependent one, so things like skin effect and core losses. but we also get an equivalent parallel capacitance. Usually the datasheet will not mention this, however it will mention the SRF, the self-resonant frequency. And well, from this, you can derive the parallel capacitance yourself. The importance of this parameter lies in the way in which it impacts the inductor's impedance. So, an ideal inductor has a constantly rising impedance, but the real one has a peak at the self-resonance frequency, after which the impedance drops as it starts to behave capacitively. In other words, if we apply a uniform noise spectrum to a real inductor in series, the noise will be more and more attenuated up until this self-resonant frequency, and then it will start to increase again. So if the SRF is low enough, a lot of the high-frequency noise content of the switching node will simply jump over the inductor and arrive at the output. And now you don't want that, do you? We can easily see this in the simulator. So for this, I took the test circuit for the LTC3542, a buck converter, and created 3 different implementations. Now, all 3 circuits have the same realistic capacitor, so a component which, other than the capacitance, also has ESR and ESL, but the difference in between the 3 circuits is the inductor. So the first inductor is an idealized one. It just has inductance, and well, the default series resistance of 1 milliohm, but the other 2 also have some parallel capacitance added. So the first one has 1 picofarad, and the other one has 5 picofarads. Now, to put this into perspective, the added capacitance makes the first inductor have a self-resonant frequency of 107 MHz, and the second one has 48 MHz. So even with these values, these are both pretty good inductors. Now, if we simulate, and we check the noise present on the output, so let's just zoom in a bit to get a clearer picture. With our ideal inductor, we are getting pretty decent waveforms. The ripple is impacted by the ESR and the exact capacitance value, but nothing much else interesting is happening. But now, if we go for the circuits that have the realistic inductors, so first off, the one with the 1 picofarad parallel capacitance, we see more or less the same waveform, but we also have these high-frequency spikes appearing. And these are somewhere in the 14-15 millivolts peak-to-peak range. Now finally, if we go for the circuit with the larger parallel capacitance, well, we get again the same waveform, but the spikes are much bigger this time. So now, the noise increased to the 70-something millivolt range. So the more capacitance we have, the more of the noise from the switching node passes through. Now, we can look at this problem in another way by simulating the inductor and the output capacitance using an AC noise source. So without the rest of the converter, just to keep things simple. So if we look at the output transfer function of this sort of circuit, we can see how an ideal inductor and capacitor have an attenuating characteristic up until the ESR becomes the limit, so then the filter flatlines. But if we also include the parallel capacitance, we get more or less the same behavior up until the point where we don't. So at very high frequencies, the attenuation starts to decrease, and more of the noise can pass through. And while with more capacitance, the effect becomes visible at lower frequencies. So as long as both the inductor and the capacitor are modeled accurately, you should be able to get a good idea of their combined filtering effectiveness by using the simplified analysis. And well, if you have the complete switch mode power supply model, you can also check the complete circuit for the best results. The last aspect to discuss is a bit more tricky, and it has to do with the way in which the inductor is physically built. So when you're coiling a coil, you need to start somewhere and then add the turns. Shocking, I know, but at the end, you need to take your wire back to the terminal, and well, you're done. Now, from an electrical point of view, the inductor is symmetrical. Whether you measure it one way or the other, it gives the same values. However, it's not the same from an electromagnetic point of view, or well, from a noise analysis point of view. So, if we draw a vertical inductor with a starting point and an end point, the 2 pins, in isolation, are identical. However, if we consider the environment around it, there is a major difference in the capacitance from each pin towards the environment. The first pin has a weaker coupling than the second one, since that one is further away. This behavior is more enhanced in multilayer coils, where the first pin of the circuit goes to the inner layer, and while the outer layer covers this. The end effect is that the inductor is no longer symmetrical. So, from an electrical noise point of view, based on how you place your inductor in the circuit, the observable noise will be larger if the starting point of the inductor is not in the noisy part of the circuit. Or at least that's the theory anyway. To highlight this, I took the board we previously used, put back the noisy ferrite core, and created a setup to measure the electrical fields this time. So I made a crude E-field probe from the plastic box I had, and put everything in a shielded enclosure. Then, after measuring the electrical field at a given distance, we get, well, a certain amount of noise. Now, if I rotate the inductor, so everything is the same, I'm using the same inductor, just rotated, and while we remeasure, we get this. So now just to zoom in cyan I have the noise floor, in pink I have the first inductor, and in yellow the second inductor. Well, there's not that clear of a difference. There is a bit of a difference at relatively low frequencies, but the high frequency part seems to be more or less the same. However, in a different situation, you might get a completely different result. So with certain inductors and certain setups, orientation will matter quite a lot. In this case, well, the difference was not really that obvious. But anyway, inductor orientation is something to keep in mind. Let's now turn to the other main reactive element found in any power supply, the capacitor. Now, although in some cases a single component can be used, usually you will find that capacitors come in sets of 2, 3, or even more. Let's now see why that is. So fundamentally, the capacitor has two main functions. It's first of all an energy storage element. Since the supply is connected with very low impedance connections to it, the capacitor is the local place from which the supply pulls energy from, and it's also an output buffer to smooth out the energy that is being delivered to the load. And secondly, it's also a noise filter. It's supposed to have a low impedance to short out the pesky noise and prevent it from exiting the converter. Now, when designing a power supply, the determination of the exact capacitor configuration requires that you go through multiple steps. First, you need to consider transient loads, moments in which the output of the converter transitions between extreme current consumptions. So, since the converter cannot instantaneously provide or stop providing energy, a large capacitor is used as a buffer to give time to the feedback loop to react and reduce the otherwise severe overshoots or undershoots that could occur. From a timescale point of view, these transients occur at a far lower frequency than the switching frequency, and while to mitigate these, you will need large values of capacitance, preferably with relatively low ESR. The next phenomenon to consider is the switching frequency itself and the pulsating current going through the converter. From an amplitude point of view, this can be smaller or larger than the transients we looked at previously, but this occurs at a much higher frequency. Here again we need a low value of ESR and a somewhat medium value of capacitance. However, since the current is smaller and the frequency higher, the capacitance needed for this specific point is lower than for the previous point. Finally, the capacitor is used to filter out the high frequency noise present in the converter, appearing from the switch transitions and various ringings that could appear. Here, we just want a low total impedance value without any regard for the exact capacitance or ESR. However, because of the frequency at which we are working, which could be 1 or 2 or 3 orders of magnitude above the switching frequency, achieving this low impedance is easier said than done. So, to cover all 3 of these cases, you might get away with a single capacitor if requirements are not that steep and you're lucky, or you could have multiple components in parallel, each one covering parts of the requirement. Let's now look at some of the common multi-component implementations that you will find. So the first common use case to look at are mains power supplies. Here, the input voltage is high, and it's pulsating to begin with, somewhere between 50 and 120 Hz, depending on the region and the rectification scheme. So you will need very large capacitor values, and only electrolytics are practical for this task. Now, because the electrolytics have a very poor high-frequency behavior, and ceramics with large capacitance values rated for high voltages are pretty expensive, you will most commonly find film capacitors. Regarding the choice of capacitor, it's important to remember that part of the reason for a capacitor's equivalent series inductance are its terminals, and the way in which it's connected to the board. So even if you do have a fancy ceramic, if it has long leads, it will inevitably have a lot of ESL. So usually the film capacitor is the best price to performance choice. Next, let's look at the output of the typical mains converter. So this is different since we are now typically working with much lower voltages. So you will still find the electrolytic needed to provide a large energy buffer, but now, for noise filtration purposes, the film capacitor is replaced by a ceramic. In this use case, it can provide better performance in a smaller package. Now, another important category of converters is used to take one DC voltage to another, usually both being relatively low. In this case, the converters are working at higher frequencies, usually hundreds of kilohertz, and here the typical aluminum electrolytics are quite rare, since usually they are replaced by lower ESR versions like the polymer electrolytics or tantalum capacitors. And since the voltages are also relatively low, ceramics are more and more common, with relatively large values being easily affordable nowadays. Finally, as converters move into the megahertz switching range, electrolytics are more and more rare, and the entire capacitance bank is achieved with ceramics. Since you can't really put an infinite amount of capacitance into a single package, you will see rows of capacitors in parallel. This both provides a large value of capacitance, but also it ensures a low total equivalent series resistance and a low impedance at high frequency. Now, when combining capacitors, it's important to observe that the total impedance you get when combining multiple individual capacitors in parallel may not always be the value that you actually want to get. So to highlight this, I created some simulation circuits using generic component models that represent a 22 microfarad tantalum capacitor, a 4.7 microfarad ceramic capacitor in a large case size, and a 100 nanofarad capacitor in a small case size. So if we run the circuit and we look at their impedance, so I'm injecting a constant current of 1, and the impedance is equal to the voltage in this case. So first off, with the large bulk capacitors, although they present a very low impedance at low frequency, this quickly changes as frequencies go up. So after about 10 MHz for this particular circuit, the capacitors start behaving inductively and their impedance rises. Now, if we add in, say, our large ceramic capacitor, things do improve, but mainly at high frequency. So the low frequency behavior is not really affected, but we did push our high frequency impedance a bit lower. But now, if we also add in a 100 nanofarad capacitor, so every circuit needs an extra 100 nanofarad capacitor, we get both a better and worse result. So let's just remove the first trace, and we can see that the very high frequency behavior is better, impedance was pushed lower, but there is a specific region in which adding in this extra capacitor made things worse. So because the series inductance from one capacitor can interact with the capacitance from the other capacitor, we can get anti-resonances. So these create zones with high impedance. So in the complete impedance curve of the total capacitor bank, adding in capacitors could make things worse in specific places. And if this happens, the ripple can get higher than would have been expected when you first chose the capacitors. Just to highlight this behavior, I took the supply from earlier and measured its output noise using multiple capacitor setups. So I would measure, change the setup a bit, and measure again. Anyway, after doing that a few times, Here are some results. So I started off with a double 22 microfarad tantalum capacitor and measured the noise both with a 20 MHz limited bandwidth as well as with full bandwidth. And well, we are getting noise. Around 55 millivolts of ripple and up to 500 millivolts of high frequency spikes. Now, if I add in a low impedance ceramic, say a large 4.7 microfarad 1206 capacitor, noise does indeed decrease. The ripple is down by about 12 millivolts, but the high frequency part is less than half. But next, just to highlight the impact of low impedance, I removed the 1206 and put in a single 100 nanofarad ceramic capacitor in a small package. And well, things are not all that different. We are seeing similar values, both with the ripple and in the high frequency noise. Finally, I combined all three capacitor values, and well, I got the smallest value in the high frequency noise bit, but we still see some oscillations appearing in the ripple. So it's still not a perfect combination yet, fine-tuning and removal of anti-resonances is still needed, but this just goes to show that adding in multiple capacitor values that work over different frequency ranges is quite an important part in power supply design. In the end, the choice of the reactive components in a switching converter, and well, any circuit in general, needs to take into account not just the component's value, its main parameter, but also secondary matrix, like parasitic elements and the exact construction. All of these factors will come into play when designing circuits with strict requirements, and a simple choice between two seemingly identical components can mean the difference between a compliant and a non-compliant circuit. So next time, we will look at some more components, specifically the actives. But until then, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.